Dr. Green is a researcher in the Department of Civil and Environmental Engineering at UC Davis. His interests cover a broad range of air quality and water quality topics, including collaborations with agricultural and clinical researchers. Dr. Green has a BS in chemistry and a PhD in physical chemistry. Over the last 10 years, he and his colleagues have tackled the question of ozone formation potential from the volatile organic compounds that arise from a wide range of agriculture-related sources, including animal agriculture, the use of solvent-based pesticides in orchards, composting, and biosolids composting. So I'm very pleased to have him speak with us today. Peter, go ahead.
Okay, thank you very much for the invitation. And at the front page here you can see my email addresses, and I'd be happy to follow up with anyone later if you have other questions that come to mind. Also, this talk is entirely public information, either from public sources or things that we've published in journals. So if anyone would like a copy of it, I'd be happy to send it to them if anyone just asks. And I also need to acknowledge the bottom half of the slide, the many sources of funding for this wide variety of projects, including all of you and me and my family, the taxpayers of the United States, via the USDA and EPA, California agencies, Department of Food and Ag and CalRecycle, as well as significantly private companies and a couple of nonprofit agencies, and we've had considerable in-kind support from local governments, cities and counties, as well as university extension staff. So this has been an enormous range of effort and support for which I and all my colleagues are very grateful. And speaking of my colleagues, many people have been involved in these projects over the years, including Dr. Cody Howard, who earned his PhD here. And if you want to search for our published journal articles, since my name Green is rather common, I recommend you search for a Green plus Kleeman or Green plus Mittliner. That'll narrow it down a whole lot for our recent publications. Or just email me and say, hey, I'd like to hear more about such, and I can send you the paper. Oh, and I should also add at the bottom, we've had enormous help from members of state agencies as well as US EPA, who have really contributed in a very meaningful and significant way to these projects. This wasn't just me, my colleagues here, and students, but it really involved a lot of good participation from those folks. So as an outline, I'll talk first about the importance of ozone and the precursors that lead to ozone formation down here at ground level, where it's an air quality challenge, and then run through the many projects we've been doing with some emphasis on the more important ones. I will do some comparison of agricultural versus non-agricultural sources of precursors to ozone, because that's a big question, how to differentiate the two, how to assess which is more important, and how to make progress on air quality. And so I'll go into some detail on several of the projects, not all of them, and then offer some conclusions. So first, ground level ozone is a secondary pollutant, and that makes it tough to work on because, except for a few rare cases, it's not emitted directly. It occurs indirectly from the emissions and then subsequent reactions of other primary pollutants or primary emissions. So you're solving a puzzle with some of the pieces and looking at what happens when they're put together. And to simplify, of course, there are three initial ingredients. The first, volatile organic compounds, abbreviated VOCs, and it's not quite a synonym, but it's close, reactive organic gases, or ROGs. And these are definitely both naturally occurring as well as anthropogenic. They can include the lovely scent of trees and bushes and grass, as well as spilled gasoline and the incomplete combustion from engines. Nitrogen oxides are also to small degrees found in natural sources, but are definitely primarily from combustion, particularly in any region with a substantial human population and human activity. And then sunlight is needed, and that's entirely provided naturally. And ironically, if you have more dust in the air, more soot, or natural dust, say from a volcanic eruption or something, you can provide some shade and limit the sunlight. And in reality, that will reduce the amount of ozone that's formed, and since ozone is detrimental, that would be a good thing. However, putting more soot, dust, other aerosols in the air is to most people's opinion, and for health effects, not a good way to solve the ozone problem. So we want to figure it out by figuring it out what are the gas reactants and which of them we can reduce and therefore lessen the formation of ozone. So here's a big list of 10 projects over about the last 10 years. They're in chronological order, and we have a couple more in progress. They're each very complicated. Each could be a whole 20-minute talk. So what I'll do is try to hit some highlights, particularly the ones that have a little asterisk on the left side there, ones that led to surprising results, unexpected results, both significant and surprisingly insignificant in some cases. Others I'm just listing for completeness so that you can see what we've tackled from the various funding sources and the importance of improving air quality here in California. We've been looking at all kinds of things to see what their role might be or might not be. So this includes the very big dairy industry in California at the top, the use of aromatic solvents for spraying insecticides in orchards, the use of pesticidal oils, which is very large in mass but very minimal in terms of air impact, studies of other livestock, so beyond cattle, pigs, and poultry, and in all these studies, the animals themselves, their fresh waste, and then we zeroed in on what was actually a very important VOC source, fermented animal feed, most importantly corn silage. We've looked at composting, which is very pungent. If you've ever done backyard composting or seen a compost pile or even shopped for a bag of compost at your local hardware or garden store, it's very pungent, and a lot of that is VOCs, but a lot of it's very low reactivity. We also looked at biosolids, co-composting. Biosolids are from wastewater treatment plants. It starts out as sludge, and then once it's aged for a while, it's called biosolids, which is a much nicer word. And we've then gone into some more detailed studies, reactivity of aromatic solvents, the ones that are used in insecticide spraying as well as a fumigant, particularly under different atmospheric conditions. This was a laboratory study, but important for where things are going in the future as the background concentrations of NOx improve, which they are steadily doing so. Finally, we're just wrapping up an EPA report on the emission of NOx itself during the process of fermentation of material like corn to make what's called silage, a preserved animal feed, and looking at the chemical mechanism. And it's tricky, but it's interesting and quite important. Finally, a study that I'm just sort of in the middle of is the land application of green waste. That would be things like lawn mowing, prunings, agricultural clippings, not yet composted, and their emission of greenhouse gases, as well as VOCs. So because of the concern of greenhouse gas emissions, we are starting to include that in a lot of our studies because we don't want to be solving one problem but making another problem bigger. So besides California, where in the United States are there ozone challenges? These are the counties in the United States that are in non-attainment as of last winter when I downloaded this from the EPA website. A lot of them are in blue or yellow, so marginal to moderate, not that far in exceedance and not that many days of the year. And in California, particularly the Central Valley of California and Southern California, the greater Los Angeles area have what's called extreme non-attainment. So many days of exceedance. And what you notice is that by and large, all the major cities in the United States have an ozone problem. So that's from human activity and focused on urban areas. It's an urban phenomenon. So human activity in general, but particularly combustion, both gasoline and diesel engines play a role. You do notice some interesting outliers. This area of western Wyoming is very unpopulated, but it has a huge boom in fossil fuel production, and therefore a lot of new human activity in recent years, including a lot of diesel engines, drilling and pumping and processing. And as a result, they're actually getting some significant exceedances. The other thing you might notice on this map is that larger cities in the north, so Seattle, Portland, Minneapolis, for example, aren't shown. And that's because the further north you go, the sun is not so high in the sky, you don't get as much ultraviolet light, and it's the ultraviolet end of the sunlight that more significantly promotes ozone formation. So being north gives you a bit of a break. It also is noticeable that a big city like Miami does not have a problem. That's because there's a sea breeze all the time, as well as a lot of clouds and rain in the summer. If they had an offshore monitoring station, maybe 10, 20 miles offshore, where the photochemistry could occur and make ozone, maybe they would have exceedances, but there's nobody there. So it's a matter of geography and climate. And what we have in California is a lot of people, almost as many people as in the populated Northeast corridor of the U.S., but a very much more of a dry, sunny climate. And with a lack of clouds, lack of rain to clear things out, as well as mountains that trap the air, we end up with a much more serious ozone problem. And it's a very intense agricultural area, that big flat valley that gets water from those nice mountains. And that's what we're up against. So just to repeat the point of where the people are is where the air quality problems are. Here's a simple map of population density of the United States. All of the big cities in dark red and relatively densely populated areas. And by and large, it's a similar map, with the exceptions that I mentioned in the north, or where there's a nice sea breeze, and certainly in Florida there are no mountains, not even small hills to trap the air. It all just blows away. So we've been aware of this for a long time. The Clean Air Act goes back decades, and California has been leading the way with the Air Resources Board since even before the federal government got rolling on these kind of issues. And indeed, there's been huge improvement by cleaning up cars, having their emissions reduced, working on power plants and other sources. So you see, with year-to-year variation, a very steady decline of the peak ozone concentrations, although still not nearly reaching the low level that is the legal requirement, either national or state, which is a little more stringent at the moment. And the San Joaquin Valley, which is the southern half of the Central Valley of California, and one of the most productive agricultural regions anywhere on Earth, they never had such high concentrations of ozone as the urban areas like Los Angeles. However, during the same period of time where cars were becoming cleaner in power plants, and now even diesel engines on trucks and so on, the progress has been much slower. And so over time that led to the question, well, are there other sources that are important leading to ozone that we're not aware of and that we need to do something about? And I should add, there's a note here. This looks pretty slow, but these are the peak readings at any monitoring site. And the number of monitoring sites, the area that's experiencing high ozone, has been shrinking also. So it's doing better than it looks. It's just that we don't meet the legal requirement until no monitoring site is exceeding ozone even on a single day. And here's a nice Google map of the southern half of California, roughly speaking. This is the big southern half of the Central Valley, this so-called San Joaquin Valley. Nice and green here. It must have been a good wet year when they took this picture. Lots of agriculture thriving. And by comparison, here's Los Angeles. I believe it's at the same scale. And Los Angeles has 6 times the population, let's say 18 million people in that snapshot, versus about 3 million people spread out over this much larger area, several times larger. So the human impact is a lot more dilute, but the geography is much tougher. Right along here are the tallest mountains in the contiguous 48 states, and those mountains completely encircle that valley with an opening at the upwind end, and the upwind end comes from a couple million people in the Bay Area where I grew up. So some of those emissions creep in. So the incoming air is not as clean as one might like, and then it gets trapped, and so it has plenty of time to react. And so geography that ironically makes this a fantastic agricultural area, a flat, warm valley with very, very little frost even in the winter, and a supply of melting snow for water all summer long with pure sunshine. It's fantastic for agriculture. What more could you want but flat land, warm sunshine, and water? Whether you're growing plants or dairy production. The trouble is that that's a recipe for very challenging air quality issues. Perhaps the most challenging geography anywhere on Earth, and certainly the only place with a few million people doing very productive agriculture. Now, the number of days I mentioned, the law says you're not supposed to exceed this at all, and it's one thing for an eastern city or a central U.S. city to have a bad heat wave in the summer and they have 10 or 20 days where they exceed ozone standard. The data in California going back to past measurements of ozone but using the current standard for air quality, it's a couple hundred days. That's half of the entire year, more than half of the entire year. Down to recently we're getting, for Los Angeles close to just 100 days, which, that's actually a rather large number. That's 3 months of air quality exceedances. Even if they're only exceeding a little, that's not allowed and that's not close to zero. The San Joaquin Valley was never quite so high. It was never over 200, but also has been declining only very slowly. And it's actually striking. You can see the variation. Some of these were wet years with a lot of rain, with El Nino weather pattern here and here. So a lot of it is weather related, and that's nothing one can do anything about. But the seriousness of why these are labeled as extreme non-attainment is honest. When you're exceeding a Clean Air Act national air quality standard by 100 days a year, at least at one or more monitoring sites, that is serious. So where does this all come from? Ozone comes from VOCs, NOx, and of course the sunlight we have lots of. Today's a beautiful hot day in the 90s here. We're going to be in the 90s by this afternoon. In an urban area, the Air Resources Board, which has been tallying and inventorying these things for a long time, can tell you the leading sources, even though they're a lot cleaner than they used to be, is still light-duty cars, other consumer products, boats, which are not so clean, off-road equipment, also not so clean, lawnmowers and leaf blowers, various paints, and on and on and on. You go a long way down this list before you see anything agricultural, down about number 23, 22, and animal waste and pesticides down at the very bottom of the top 25. So in an urban area, it's still non-agricultural activity. No question about it. Although those other sources, they could be cleaner too. That would help. In an agricultural region, such as the San Joaquin Valley, it's different. Cars may still be in the lead, although they're getting cleaner year by year, so they keep shrinking. In fact, several percent per year in absolute magnitude. So their relative share of that slice of the pie will be declining. And even back in 2005, when we were starting to focus on the dairy industry, they had marked livestock waste from the dairy cattle as the number 2 source of VOCs, which are one of the key precursors to ozone formation. So that's remarkable. So that is agriculture. And then number 5 was pesticides. So that's how we got going on some of this. The NOx emissions, which are the other key ingredient, look, well, a little different, but a little similar. Heavy-duty diesel trucks from the major highways going through the region, they were in the lead, although that's, again, been declining very, very steadily and successfully as engines are retrofitted or replaced. But diesel engines last a long time, which is a great thing, but it means that their cleanup is not so fast as personal vehicles, which turn over more quickly. But number 2 actually were farm equipment, so tractors and such, harvesters, pesticide sprayers that emit NOx, and they don't have emissions controls, and they last a long, long time. So the agricultural role, even though it's the equipment role, not the plants or animals themselves, was at this time considered number 2. And unless it's also getting the attention to clean it up, it will gradually climb in importance. So what we've been doing in almost all of these projects, a few of our projects have been laboratory experiments, but almost all of them have been field experiments. We go out and collect gas samples and characterize all the VOCs that are there, and we take with us an ozone chamber, and we take a sample of the air that's there at the location, whether it's a dairy operation or pesticide spraying at an orchard or a composting facility, and in a clean Teflon bag with lamps for illuminating to simulate sunlight, see how much ozone forms. And then we match by calculation based on the VOCs we saw and the background amount of NOx, did the amount of ozone that formed make sense with what we saw in the chamber? And if not, then we go back to the drawing board and figure out what we're missing. But generally speaking, after a few tries early on, we got it to match up pretty well. So we believe we do know how the ozone is forming and from which VOCs, and that's really rarely been done anywhere with an ozone, a movable ozone chamber. And here's a picture out in an orchard. There's an orchard just being set up with one of our weather stations. The work we were doing was in the established orchard. This is one of our ozone chambers. It's a Teflon bag inside a wooden box with lamps inside and a fan for temperature control and various instruments. That's a picture of the big spraying machine that was doing the insecticide spraying. You can see the mist out there, and that's our second ozone chamber. One of them on the upwind side, one of them on the downwind side of the orchard, in as much as the wind would cooperate. And so there's going to be a quiz later, so you all need to take notes quickly, write this down, and get the names and numbers correct for these VOCs. These are the many VOCs we were able to detect at orchards with 4 different experiments. These are the samples we collected in the morning after they had done overnight spraying, and it includes all kinds of compounds from various sources, and I'll get to that in a moment. Even including, with such sensitive equipment, tiny amounts of the long band CFCs, because they're still there. It's not that they have anything to do with the orchard; they're just in the air. The much simpler summary is here. The solvent that was used to deliver the insecticide was present at a modest level in the background the day before. And that's because either it was sprayed previously, either at that location or somewhere upwind, or the same molecule comes from some other source, such as a vehicle fuel, which is possible. But then after the overnight spraying, when we took samples in the morning, there was more of it. So we could definitely tell, although it's not that large a change as one might think. And then a day later, it was down, and after this study, this particular graph I'm showing you, we went to a second day, 2 days after spraying, and see things roughly back to the background level. So these molecules are there anyway, but more of them do show up when the solvent is sprayed. It's only, I'm trying to remember the numbers, maybe 1 liter per acre of solvent, in that range. But more important, we could see the biogenic compounds, things from the disturbance of the orchard itself, various terpenes and similar compounds. Because of the spraying on the trees, they emitted a lot. For example, a citrus orchard smells like a wonderful, lemony scent, and there will be more of it after you've gone through with a big strong fan and sprayed and disturbed it. But even more significant, far more significant, you can see the fuel, either unburnt at all or incompletely combusted fuel, from the spraying vehicle was by far the largest amount of VOCs that occurred at the time of the spraying. So to have less ozone, one needs a cleaner vehicle doing the spraying. And once that's been cleaned up, then you can start thinking about, well, could we change this from a solvent-based insecticide to a non-solvent-based insecticide? So on to composting. These are not your little backyard compost piles. These are huge. Those are regular-sized people on top and over on the right by the equipment. That's a regular-sized pickup truck. And this facility went on for acres. This was a municipal facility for a city in the San Joaquin Valley. They collect all the trimmings from all kinds of landscaping businesses and their own operations. They compost it, and all of it gets used. It's fully subscribed. It's a very productive reuse of material. But it's very pungent, and it is an emission of VOCs. In fact, large masses of VOCs. The question is what are those VOCs? How much ozone do they make? So here's your second test. I don't have the concentrations there. You just have to get the names right, so start memorizing. I can simplify the whole thing by pointing right in close on one of these at the lower center, methanol, whose traditional name is wood alcohol. That's the main VOC coming out of the microbial decomposition of woody wastes. And it's not very reactive. In fact, if you go around the world and take air samples away from human activity, it's the main VOC that you'll find because it's not very reactive, so it lasts a long time. So whenever there's grass or bushes or trees decomposing, which is what happens in life, you get methanol. And the other more reactive things like the terpenes don't travel very far. So we could publish the statement that yes, these are VOCs, and yes, there's a ton of them, but by and large, it's not going to make a whole lot of ozone. And if you were to mitigate it by having some kind of a diesel engine put a cover tarp over all of this repeatedly after it was turned and rewatered during the normal composting process, the detrimental emissions from that engine would plausibly be worse than the left alone natural, quote natural, it's human activity, but it's a somewhat natural process of composting that would lead to ozone. Next, on to animal feed. Once again, these are regular-sized people, and I hope it gives you an idea how large agriculture can be. That's a pile of chopped up corn that's been compacted and kept anaerobic under tarps, and those are old tires on top. Originally it was all in a completely covered hill while it fermented or pickled. The term is ensiling, to make silage. And then in the course of the year, a big truck comes and takes a scoop and carries it out to the animals to feed them. It's a fantastic way to preserve animal feed. If you think of human food, normally we have to store things either dry or refrigerated, or sealed up in a can somehow to keep the air out. Well, this is kind of like sealed up to keep the air out, and it lasts for a year. But when it's opened up like this, you can imagine a huge amount of vapor emissions from such a big, rough face of fermented, chopped up corn, and particularly in a hot, dry, and especially if there's a breeze, summer climate. And it turns out that if you look at all the mass of animal feed being used in the San Joaquin Valley of California, I mentioned there are about 3 million people in the San Joaquin Valley. There are also about 3 million cows. And if you're aware, cows are larger. So their food per day, feed I should say, their feed, our food, is much larger. And it's just typically taken a lot of it from these kind of open or semi-open piles and placed in front of the animals. So a lot is offered to evaporate. And those emissions are significant. And in the paper we published in 2010 with Cody Howard as the first author, we estimated with some uncertainty that the total animal feed, particularly from the corn silage, based on the practices that were documented to be representative at that time, was, within uncertainty, probably larger than the ozone production from the VOCs from light-duty vehicles, so passenger cars. So that's spectacular to say that the emissions from animal feed, it's not the animal itself, it's the feed and its handling, could already be larger than light-duty vehicles by that date. And with the light-duty vehicles getting cleaner and cleaner and cleaner as the years go by, people buy cars with better mileage, new cars are cleaner than old cars, and smog checks and so on that keep them clean are maintained. This was quite a big deal. And this was a big surprise. So going over some of the unexpected results, the composting, which is so pungent, has a low reactivity, was unexpected. That the pesticides were more of a problem from the vehicle doing the spraying rather than the pesticide solvent itself, that was unexpected. And here, that the animal feed could actually be more of an ozone precursor source than all the light-duty vehicles with 3 million people in an air basin. It was unexpected and remarkable. And incorrect in that, if you remember that Air Resources Board inventory, they had the animal waste listed as the leading agricultural source of VOC emissions in the San Joaquin Valley, and it wasn't the animal waste at all. That again, we studied, and it's actually fairly low reactivity, another unexpected result. The animal waste, the primary VOC, was ethanol from fermentation, and ethanol, like methanol, has a fairly low reactivity. So here we have a series of unexpected results, some positive, some negative. And this has raised a lot of attention in the business. Here's a little more detail from a figure from that paper showing that what was important was that in the corn silage, for example, you have a mixture of many different VOCs, and then from the other components of silage and the total mixed ration here, we were able to subdivide the different components and model how much ozone they would form and get a fairly good match for what the total would be. And that the take-home message is that sometimes the most abundant VOC, the one with the most pounds, is not the one that's making the most of the final ozone, which is the air quality pollutant we're trying to reduce. The Clean Air Act still considers all reactive VOCs to be equal, even though they're known to have different reactivities. It's difficult and a tricky, long legislative story. But it's another unexpected result that the main thing present on a pound basis isn't the main thing causing the air quality problem. The ethanol may be the main pounds, but it'll be other compounds like aldehydes and some olefins that lead to more of the ozone. One other study we've been looking at is the fumigant chloropicrin. There are only a few fumigants, gases that are used to sterilize the subsurface soil, particularly in California in the strawberry industry, also orchards like almonds and peach, as far as I recall. And this is a unique compound in the class because it has an NO2 group. So when it if it does escape from the subsurface, and a small percentage will, no matter how carefully things are done, that will actually break off and add NO2 to the atmosphere. So adding the other ingredient to ozone formation. And so we've been studying that. Okay, so let me get to some conclusions and then have lots of time for questions. One of the big issues that was outstanding a decade ago was how can you possibly figure out where the ozone is coming from, given that it's a secondary pollutant, and given that some of these sources, like animals themselves, their waste, animal feed, spraying in a pesticide orchard, spraying pesticides in an orchard, composting, and then I mentioned briefly the co-composting of biosolids with compost. How can you possibly figure out where the ozone is coming from and which precursors are responsible? Well, if you take an ozone chamber to the field like we did and collect samples by various means, do the chemical measurements, do the modeling, observe the actual ozone formation over a period of hours, and we would typically do replicates morning and afternoon for a few days. And again, once we got enough expertise and we're able to match these things up, we can say, yes, these are the VOCs present, and these account for the total amount of ozone that occurred, and which of those VOCs is the stronger or weaker source. And that's been, I think, our big contribution to the field. And it's had, as I say, unexpected results, cases where what was thought to be the problem wasn't the problem, like the animal waste or perhaps the pesticide solvent. But what was the problem was something else, the animal feed, which was not even in the inventory to be tallied as a possible source for decades. It wasn't even on the list. And the vehicle doing the spraying, now of course the vehicle comes under different legislation, different regulatory control, so that's difficult. But we're not writing regulations here, we're just trying to identify what things contribute to what, and therefore hopefully point the way. So this effort was tricky and tough on all the different projects, but I think it's necessary to make sure that mitigation of VOCs actually helps ozone decline. For example, one could spend a lot of effort, as I described, bringing in engines and covering tarps over composting piles, and that wouldn't even help much because the engines could be a net loss against what you're limiting. Similarly, you could focus intensely on animal feed, animal waste, which has a bad odor, and of course odor is another air quality issue, but not an ozone precursor, and miss the fact that it's the animal feed that's the much stronger source. And also, it's important to realize economically, we want to solve the problem wisely. The loss of animal feed by evaporation out of an open pile like that can be a loss of 20 or 30% of the nutritive organic matter that should go to the animal. And the animal feed is the main cost at a dairy operation. It's the main thing that's happening. It's much more than their electric bill or their water bill or their labor or their veterinary bills, whatever other things come up, documentation, regulations, adherence. It's the feed. And if they're losing 20 or 30% of the main cost at a business, well, that's enormous. If they could cut that in half, that's a huge difference economically. So finding the main source of the VOCs that lead to ozone also points to a huge opportunity for economic improvement, and there are a lot of efforts going in that direction already. Keeping things more covered, keeping things packaged in a long plastic tube, very large tube, like 12-foot diameter. It's called a silage bag sometimes. Anyway, practical solutions are part of our overall effort, and the implementation is a challenge because the law as written will say that the low reactivity compounds like methanol and ethanol legally have to be counted the same as the high reactivity compounds such as aldehydes or alkenes. However, it is within the flexibility of mitigation and implementation plans to have the total pounds of emissions go down, but know more wisely that one can look at the reactivity-weighted pounds and make sure those go down more efficiently, more quickly, or more cost-effectively. That way, the air quality will get better, because if we can meet air quality standards, well, then we're free from this challenge, and life can go on without such concerns. And it's going to be a long time coming, but still, that is the goal. Again, to emphasize here, for the San Joaquin Valley, the strongest agricultural source of ozone-forming VOC emissions was not being inventoried at all, the animal feed, much less studied and mitigated. So that's extraordinary for a region like California, which has been studying all sorts of air quality emissions for a long, long time, and highly aware of what these things might be leading to. But no one had put enough of the 2 and 2 together to find that fact. So our biggest surprise, perhaps. More conclusions. Agriculture certainly has an important role in improving air quality, not just here, but everywhere. And increasingly, this involves things like greenhouse gases, NOx emissions directly from vehicles, and actually the fermented animal feed, the VOCs. Ammonia is a big deal, I'm well aware, for direct effects and secondary aerosol formation. Dust and odor, very important nuisance issues. So one has to look at all of these together. Significantly, agriculture involves NOx from the combustion of a lot of engines, which is just one form of human activity. And particularly in California, I don't know about elsewhere, the fumigant chloropicrin is a surprising NOx source. So the VOC reductions need to focus on specific VOCs. They can't legally be claimed exempt without impossible hurdles to overcome. But the specific reductions, as well as total pound reductions, need to be borne in mind. Regional EPA folks here understand this well. At the federal level, well, I don't know, it's getting there. Silage, the fermented animal feed, is really the only strong agriculture-related VOC source we've been able to find. NOx emissions are currently under study, and certainly NOx from vehicles involved in agriculture is important. And quite certainly in California and in many other states and countries. Future regulations will look at greenhouse gas reductions along with other control efforts. So one doesn't want to be making progress on one issue but losing ground on another. So thank you very much. I'll be happy to take any questions now. And also those are my 2 email addresses. I'd be happy to respond to questions anytime later, send you a copy of this talk, or send you a paper or 2, or however many I can fit into an email. Thank you very much.